Hello, everyone. I hope you had a great day so far. Let's start today's session. Today, we are going to talk about the diet. This week is mostly dedicated to the as a reminder of what we learned about the diodes, like the Zener diodes and the LEDs in the circuit lab and in the other courses. So we wanted to kind of you up and remember what we learned about the diodes. So let's move on and introduce the diode, which is, come on, one of the semiconductor devices that we are going to deal with in our lab. And the diode generally is a PN semiconductor, okay, which, as you know, the purpose of the diode, the performance of the diode is to let a unidirectional current. So the diode only let the current to conduct in one direction. That one direction, we call it forward bias. So basically in forward bias, we have current. In reverse bias, we don't have any current. This is an approximation. We are going to see that. Now, I assume you're already familiar with the IV characteristics of a diode, which, as you can see in the chart, in the graph on this slide, we have two regions of working when we talk about the diode. One, as we said, is forward bias, that green region. When we apply forward voltage, and when we talk about the forward voltage, we mean a higher potential is connected to the anode and the lower potential is connected to the cathode. Okay, if we have forward bias voltage across our diode, okay, the diode will conduct current. There is another point to that. It is not like every level of the voltage would make the diode to conduct current. There is a certain threshold. Okay, if our forward bias voltage exceeds that threshold, now our diode gonna go to the conducting. Okay, we call that voltage threshold. Okay, or as you can see, we show it by V of F, voltage of the forward bias. Okay, in silicon-based diode, that voltage is 0.7 volt, and in germanium-based diode is 0.3 volt. Okay, 0.3 volt. So if you have like a sensitive circuit that you need to get to get the diode activated in a lower voltage, that says that you need to use the germanium instead of the silicon. Okay, now you already seen the symbol of the diode that we use in a schematic. Okay, one side of that diode is marked with a band, this side. This side, we call it cathode. Okay, and the other terminal is anode. So, as we said, when we have the higher potential applied to the anode and the lower potential to the cathode, that means forward bias, the current go through the diode. Okay, now the next region that we are going to talk about is reverse bias. When we want to cut the current, okay, we want to allow the current to pass through. On that part, in the reverse bias, we change the polarity of the voltage across the diode, meaning we connect the higher voltage to the cathode and the lower voltage to the anode. Are we good so far? So that is reverse bias. If we have a reverse bias, we don't have any current. Now, I said this is approximately no current. As you can see in the chart, the graph is not exactly on the zero line. So we have a little bit of a leakage, but it's so low that we basically can ignore that and consider no current in a reverse bias. Okay? But Now, as you can see, when we are in a reverse bias, at a certain point, it starts to conduct current at a certain level of the voltage. What is that? Now, the diode is not just a mathematical function or like a drawing that on a schematic. It's a physical component. Okay, so there is a limit of tolerance when it comes to voltage and current. Okay, so it's not like you can apply any level of the voltage that you want and go to like minus infinity when we have like a reverse bias. Okay, same goes to the plus infinity. So we have some like limitation because it's a physical component. Now, if we reach a certain voltage, which is above the tolerance of that physical component, that's going to burn out. That component is going to burn out, which means we call it the breakdown. So at a certain voltage, we have a breakdown of our component. That means it's not diode anymore. Okay, so we call this voltage breakdown. It's approximately like in some of the cases is like, for example, minus 50 volts. So if you exceed that, that means you exceed the tolerance of that component and it will break down. So now you don't have a diode. Ergo, your current gonna be conducted even in a reverse bias. When we talk about the general diode, we wanna avoid this region. We don't wanna even get near that region. Okay? So when you're using the diode in a reverse bias, be careful. You don't want to get even close to that breakdown voltage. Are we good so far? So this is the general idea. Now, how we can model that? You saw in IV characteristics that we have some sort of exponential growth in forward bias. Correct? So that means the current is not independent of the voltage. It would grow as a function of the voltage across the diode. But the slope of this line is so high that we can simplify it by considering a constant drop model. We can simplify it by considering like a vertical line. Okay, that would make our life much easier. So in the simplified constant drop model, now our current is not a function of our voltage anymore, the value of the current. So if we exceed the voltage threshold, which is the on voltage of the diode, okay, now the voltage stays constant, but the current can vary. The amount of current would be decided based on what's happening in the circuit. Okay, now, when we have such a model, what is the benefit of that? It helps us to, instead of having, when we want to like run the mathematical kind of like analysis over your circuit, instead of having an exponential function, a nonlinear component in your circuit, then you want to like deal with the analysis. Okay, now you have a specific constant voltage in a conducting mode. Okay, meaning you can simply replace your diode with a single voltage source. What is the value of that? That voltage threshold. So in the conducting mode, when you want to like run analysis over your circuit, you just replace the single voltage drop, the DC voltage source, equal to the V on, V threshold of that diode, that specific diode, in your circuit, and then run your circuit. Now you don't have a diode in your circuit, so you don't deal with the nonlinearities in the diode. Are we good? Now, what would happen if we have reverse bias on over our diode? Okay, or our voltage, our forward voltage is below that threshold, that V on. Now, how we can analyze a circuit that have a diode in it? Any idea? Anyone remember how we can analyze a circuit? Like, for example, we have like a voltage source, we have a reverse bias diode, and a resistor. How we can analyze this circuit? Basically, get rid of the diode. What would happen in a reverse bias to diode? Sorry? Yeah. Open circuit. Now, we are not going to get near even the voltage breakdown. So that's actually your job. You shouldn't get near the voltage breakdown. So we kind of like want to like avoid that. So that's not going to be the case that we are going to talk about in circuit analysis and right now in our lab. Okay. When you are out there after your graduation, you're designing a system, you have to consider for the voltage breakdown because you are going to have transient situation in your circuit. You should not exceed the tolerance of your diode. Okay, so that's the prompt. In this lab, we don't go near the voltage breakdown for the general diode. Now, if we are in a reverse bias or a forward bias lower than the voltage on, it's simply an open circuit. So you can replace it with open circuit and then run the analysis on whatever left on your circuit. Are we good so far? So that's how that constant drop model will simplify the analysis for us when we talk about the circuit that contains any type of diode. Now, remember, we said that like silicon base general diode is 0.7 volt as the voltage drop. The germanium is 0.3, but the LED are different. So read the datasheet of whatever diode you use. That voltage drop, the voltage should be based on the datasheet of that diode. For example, LEDs is around 2 volt, so it's different. Are we good? Now, how it works actually. We said that the diode in a forward bias after the V on would let the current pass through, okay? But in a reverse bias or below the V on, it would cut the current. How it do it? Now, when you talk about the physical structure of a component, we said the diode is a p-n junction. Between, at the point when that P semiconductor and N semiconductor are connected to each other, we have a region, we call it depletion region, that yellow region, okay? That works as an insulator. So you would not let the charges to jump from P to N or N to P. Okay? Now, if we apply the forward bias voltage, okay, what's happening in the diode is that we are forcing, because of the electrical field, we are forcing that depletion region to be smaller and smaller. Okay, to the point when we pass that V on, is small enough so the charge now could jump over that depletion. Now we have a current. On the other hand, when we have a reverse bias, that reverse electrical field that we are applying over the diode would actually increase the depletion. So we are increasing the kind of like the insulation part. Okay, so no current could pass through, no charge could jump over the depletion mode. Ergo, there is no average charge, there is no current. Is that clear? So this is kind of like the physics behind it. Okay, very simply talking about the physics behind it. Now, We have several applications when we talk about the diode. The obvious one is the rectifiers. We said the general purpose of a diode is that to make the current unidirectional. Okay, so it makes sense that one of the base application of the diode is rectifying. So it rectifies the AC, and now we have a DC current. Now, I want you to pay attention. When we talk about the DC and AC, DC would not change direction. AC would change direction, alternate. Positive half cycle, negative half cycle. That doesn't mean that in DC we don't change the voltage. We just don't cross the zero line. So this voltage is still DC. It doesn't change the direction. It has variation, but it doesn't cross the zero. Okay, so I want you to remember that. Now, another application of the diode is the clipper circuit. We are going to see the circuit of the clipper. Okay, what it does is to chop the voltage, okay, and it do not allow the voltage to go higher or lower of a certain point. Like, for example, you have a AC signal, okay, and you run a clipper, you design a clipper circuit using the diode, okay, that you basically set the maximum voltage as, for example, 3 volt, and the minimum voltage at minus 3 volt. So what the diode does is that it's not allowing the voltage to go higher than that. So it actually clip the voltage based on the threshold that you set in your circuit. We are going to see an example of the circuit of that we use for the clipper. Okay. Now, another application is the clamping. That means boosting the voltage, giving it like a DC offset. Okay, that's another application of the diode that we are going to use. Now, let's go deeper on those applications. We said diode could be used in a rectifier. We have two types of rectifier. One we call it a half-wave rectifier, which is a simple diode. Just one diode would do the work. Now, you have an AC signal as an input. You have a series diode with that source. Okay, what's happening is that when you are in a positive, for example, in this schematic, when the anode is connected to the source, if you have a positive half cycle from a certain level, remember, this is the ideal one. Okay, this shape is ideal one. This is not going to happen in reality. Okay, when you have a positive half cycle, you are in forward bias, so the current passes through. You have a voltage over your load. And when you are in a reverse bias, when the voltage of the source is negative, okay, you don't have any current conducting, so the voltage across your load is going to be zero. This is a half-wave rectifier. Now, I said this is an ideal, and it's not going to happen in reality. Now, I want to ask, we already covered that. I mentioned that several times in previous slides. What is the difference that we are going to get when we talk at the output, when we talk about the real diode, and why is the reason for that? So this is an ideal. What is going to happen in reality when we have such a schematic and the source is simple, like third AC source? What is the non-ideal, non-theoretical output that we are going to use? Sorry? That's one side, yes. I'm looking at that. I said that decay current is very small. Okay, so what's happened is that you have a little bit of negative side over there, which is very low. It's extremely low. Now, there is another important concept with that. Yeah, go on. Sorry. What planting the peak, you mean? Like, I think she's talking about like the property. Oh, the voltage on, you mean? Yeah, that's correct. We said, yeah, perfect. Yeah, we said the diode would not conduct until we pass that threshold voltage that V on. Okay, let's say this is the voltage on, like 0.7 volt for silicon-based diode. Okay, below that it doesn't conduct current. So what's happening in reality is that we have a zero here, and we start conducting. Come on, we start conducting when the voltage exceeds the 0.7. So what's happening is that we have like such a voltage. I hope you can imagine what I mean. So you would chop a little bit of that sinusoidal, which the value is below voltage on. Is that clear? So this is another problem. Yeah, go on. No, the still we have zero voltage, but what's happening, like here, you see in the blue curve, you see that immediately in a positive half cycle, the voltage is starting to increase from zero to the peak voltage. Okay, now because of V on, what's happening is that until on this region, this time, on this region, because our sinusoidal input is still below the threshold, the output remains zero and then chopped to the, after we pass the 0.7, for example, it would like you don't have a sinusoidal exactly. On this region, you still have zero. Make sense? Is that clear for everyone? So that's what's going to happen in reality. Are we good? Any question about that? No? Okay. You think your peak is no. The peak would not change. The only thing that's happening is that the diode would start conducting when the input passes the threshold. Okay, this is the input. Okay, let's say this is 0, and this is the 0.7. Okay, now what's happened is that this is 0. Here we have a forward bias voltage, but we are below the threshold, so it is still 0. At this point, at this time, now we start conducting. Again, here we get below 0, so we are gonna get 0, and then here we start conducting. Makes sense? This part is gonna be chopped down. It doesn't change the peak or frequency. It's just when the input is below the threshold, we don't have any current. There you go. The signal of output is 0. Is that clear? Any question regarding that? No? No. Beside half-wave rectifier, we have another type of rectifier, which we call it a full-wave rectifier. Now, that one, we use either 2 diode or 4 diode based on our circuit. Okay? As you can see, now in the full-wave rectifier, we don't cut the negative half cycle. We reverse it and make it positive. in the output. Now you can see that when we have a positive, see, if we have a forward bias, the current goes through here to here to here, and the circuit would be closed. Make sense? So we have the positive half cycle conducting through the load. Now, when we have negative voltage, meaning is reverse bias, this one is out, this one is out because it has reverse bias. But here, this one is conducting because now this part, this potential is higher than this one. Make sense? Is that clear? And the current goes through the diode all the way to the load. Make sense? So not only we conduct in a positive half cycle of the source, we also conduct in the negative half cycle of the source. But since the current going in the negative half cycle in that direction, that means in the load, the polarity would change, which is show itself as this one. Does that make sense? Is that clear what we talk about? Full wave rectifier? Now, the full wave rectifier is more efficient than the half wave. It's obvious because we don't chop the half cycle. We use all the energy provided by the source. Okay? And since we have multiple ripples, now the level of the voltage DC that we are going to get here would increase. It is also obvious because if we don't have this one, it's going to be 0, so the average would decrease. When we have the full wave, now the average DC voltage that we get out of our same input AC is going to be increased when we're using the full wave rectifier. Is that clear? Any question? Now, there is another type of rectifier. It works the same. As you can see, the graph shows the direction of the current. Be careful. There is a point. Look at the polarities. These two secondary windings have different direction, different polarity. Okay, so they basically change the direction of the voltage. Now, I want to ask a question. Both of them work as a full wave rectifier, okay? But there is an advantage when you use a transformer instead of directly connect the source. Anyone can remind of us about that benefit that we get if we have that transformer? Any idea? No? Okay. When we have the transformer, what's happening is that we have an electrical energy here. Through the transformer, we convert that to the magnetic energy, and then we convert it back to the electrical energy. Are we good on that? So, by this conversion, it means we are isolating the electrical characteristics of the secondary side from the electrical characteristics of the primary side. That would help us. So we could eliminate, by isolating the input and our circuit, we would eliminate the significant effect of whatever happening, a variation, whatever kind of like circuit change and impedance that the source has into our own circuit. Does that make sense? The concept of the isolation. Plus, as we know, the transformer is L. And in reality, the winding, the solenoid also has an R. So we have an RL circuit, which is a series of RL. What is the RL in series? What is the RL circuit called? When you talk about the outcome of an RL in series, what is the circuit? What does a RL in series circuit do for you? It's filter, it's low pass filter. So it would eliminate also the noises. Is that clear? So that's why this one has more advantage rather than this one. But if you just care about rectifying, both work, okay? Now, we said we have a clamper circuit and clipper circuit. So you can see if we have any offset voltage, okay, before our diode, it basically shifts the voltage for that diode. This is a clamper circuit. I want you to like go through the analysis of that. Okay, I suggest that, actually encourage you to do that and see how it actually works. Why this voltage source or any type of capacitor that we have here would help you to have a shift of a DC when you have a 0.7 here. It's actually, I gave you the answer, but you might want to like see how it would offset the system. For the clipper, if you have a series of the voltage source series with a diode, you can create a maximum amount for your values. Now, this one is forward bias, meaning it would clip the positive half cycle. This one is reverse bias, meaning it would chop the negative half cycle. If you run a KVL over that, you would find out. If you run simple, it's simple, very, very simple KVL. If you run a KVL, you would see how it works. Now, we can use the diode as a logic too, but later on, this is very simple. I don't recommend using the diode as a logic. We are gonna talk about the logic circuit when we talk about the transistor. That's a better way to create the logic circuit, but in order to be kind of like comprehensive, diodes could be used to create logic circuits. Okay? Now, we have another type of diode. So far, we only talked about the general description of a diode. Now, we have another specific type of diode. We call it a Zener diode. Okay? Which you can see the Zener diode is normally shown with these symbols. We are going to use this one. It's like that. Instead of that simple bar, we have like a reverse Z, you know, on the symbol. Okay, so when we talk about the Zener diode, the IV characteristic is still the same. In a forward bias, we are going to have a current. In reverse bias, it tries to cut the current. But what happens, because of the specific type of doping that manufacturers do for the Zener diode, we have another characteristics in a reverse bias when we're working with a Zener diode. What's happening is that we are going to be able to work on the breakdown voltage, okay, in a certain margin on the breakdown voltage without wearing out our diode. This is the physical kind of like characteristics of different doping done for the Zener diode. compared to the regular diode. Now, what that means, this is the IV characteristic that we know. Okay, when we have a Zener diode, we said we have more tolerance, okay, for basically tolerating the breakdown voltage. Okay, so we can actually reach the breakdown voltage. Okay, which basically actually the Zener diode, when we use the Zener diode, this is our goal. We want to reach the voltage to the breakdown voltage. Okay, now why is that? When you see the graph in a the IV characteristics of Zener diode in the margin near the in the interval very close to the voltage breakdown, which in this case we call it the Zener voltage. Okay, you see we have a very consistent linear behavior. Okay, there is a knee, granted, there is a exponential kind of like knee on our graph. Okay, but beside that, we have a very ideal kind of like vertical characteristics. So we could consider that like the same idea that we had for the voltage, the constant voltage drop model for the regular diode and forward bias. We can consider a constant voltage, a Zener voltage in a reverse bias for the Zener diode. Is that clear so far? That we talk what we're talking about? Now, we use, because of this characteristic, we use the Zener diode in a reverse bias to regulate the voltage and stabilize the voltage at a certain level. That certain level will be the voltage Zener, the Zener voltage of that specific diode that we use. We have different type of Zener diode. There are Zener diode that the Zener voltage is like 4.7 volt, or we have some diode that the voltage Zener is the model that voltage Zener on that model is like 5.1 volt. Okay, so different diode would stabilize, would regulate the voltage across the diode when they are in reverse bias on the specified value for that model. Am I clear? Is the statement is clear for everyone? Any question? Okay, now look at the graph. When we want to regulate the voltage, we want a stable voltage, meaning we want a voltage that are not dependent to the current. So whatever current we have, okay, we have a specific constant voltage. This is basically the main meaning of regulating the voltage. Are we good? So what that means, if you look at these characteristics, in this linear part and in this exponential part, we cannot grant that goal. So still the voltage changes with the current and changes significantly with the current. That means if we wanted to use the Zener diode as a voltage regulator, we need to avoid those. So when we wanted to like set the Zener diode, we should set the circuit in a way that we have minimum of certain current going through the Zener diode. So we would pass that knee section and go to this constant voltage drop section. So when you're working with a diode, it's not just the reverse biasing. You need to set the current above the minimum. When I say above, it's negative current, so value-wise, okay? More than the value should be more than the minimum amount of the current that you need to escape from that exponential part of the curve and go to the perfect kind of like linear vertical part of the reverse bias curve. Are we good? Now, this is the voltage breakdown. We said the Zener diode has higher tolerance when we are around the breakdown voltage than the regular diode, but that doesn't mean that they do not have any kind of like maximum value of toleration when it comes to reverse current and voltage. So when we have a certain amount, above a certain amount of power dissipation in our physical component, you can imagine that it would burn. Because there is a tolerance of how much power a physical component can conduct through itself. What that means, if we have a constant voltage and we have a toleration over power, it means we have a toleration over current. That P is VI. V is constant, so what's changing is the current. So we also have a maximum amount of current that we should not exceed, otherwise the diode is going to burn. So what's happening is that when we work with a Zener diode, we are going to set it in a reverse bias, okay? And we are going to make sure that the current passing through the Zener diode, remember, current passing through the Zener diode is not the current of the source or current of the load. Current passing through the Zener diode should be between the minimum current and maximum current. Are we good? Is that clear? So this is how we work with a Zener. Now, when you have this one of examples of a Zener diode, used for regulating the voltage. Now, at the input, we have the unregulated voltage. Okay. We use the Zener diode in reverse bias parallel to our output. Okay. And the result would be a regulated voltage equal to the Zener voltage of this Zener diode. Are we good? Now, granted, in reality, the voltage would not rigidly be constant, like if we have a 4.7 Zener diode, it's not going to happen that we always, under any condition, we have exactly 4.7, but the variation, Zener diode would stabilize the variation, okay, in a very tiny region that you can claim you have a regulated voltage. You're going to see that in the lab and in your simulation, okay, what I mean by that. Okay, so now I have, this is my output, this is my load, this is the Zener that we talked about, and this is the unregulated voltage. What is this one? You don't have the secret of the source. Normally, if you have like a function generator or any DC source, you have a DC voltage plus like 50 ohm of resistance here. Okay, I'm not considering that because we don't know what type of source you are going to use and connect this voltage. Now, this is in our voltage regulator circuit, one of the component of voltage regulator circuit. Why we have this resistance? What is the application of the resistance? The answer is over there, so we just need to like read the slide. We mentioned that worst case scenario, we should not exceed the maximum current. What is the worst case scenario? When all the current from the source passes through the Zener. So the load is open. We don't drain any current here. So this is 0, the current. So whatever current source injects goes through the zener. Correct? This is a simple case here. Now, we said we want to have a maximum current. It means, worst case scenario, we should have a resistance here that limits the current to that maximum current. So if you have, like, for example, 10 volt on your unregulated voltage source, okay, if you put 1K, that means simply you are limiting the current, the maximum amount of current passing through the resistor equal to 10 over 1K. Ohm law. Are you good? So this is how we can make sure that we are safe, our zener diode is safe. Now, when we talk about the voltage regulation, remember, the assumption is that the source is going to have a variation. That means if you have a 10 volt source, you are not going to get always a 10 volt at the output. There is going to be variation. So it's going to go higher or lower than that. What that means? That means if you calculate the resistance for exactly 10 volt, okay, there might be some situation that the current would get passes the maximum current for the zener. Is that clear? So what's going to happen is that to make sure we don't know how much the voltage would vary. Okay, that's random. Okay, so we don't know that. What we do is we apply a safety factor to make sure we never pass that I max threshold. What we do, the rule of thumb is the safety factor is 10. So if, for example, you calculate your resistor, which we call it a safe resistor, okay? And you come to the 1 kilo of resistor to meet that I max criteria, you need to apply an escalating factor, the rule of thumb is 10, and put a 10 check in your circuit. Now you are sure that we never pass, we are conservative enough, we never pass that Imax. Remember, it should not get lower than I need. So this is a trade-off. We are going to have some temperature effect when we talk about the diodes, especially zener diode. So when the temperature exceeds, the characteristics will change. I don't want to go near that because I go through that. You can search on that. We don't need that in our lab. And for our lab assignment, let's go through the exercise that we have. The first exercise is the IV characteristics. It's very simple. You have a diode in series with a safe resistor, in series with a voltage source, and you wanted to see what's going to happen. What is the characteristic, the IV characteristic of that diode? You already done that in circuit lab, so it's basically a reminder. You need to calculate the minimum resistor that you need to make sure that you're not burning out your diode yet. Is it the multiplied by 10? Yes, this is a scaling factor. Yeah. This is the safety factor is at 10 that multiplied. Next one is the LED potentiometer. Again, you have your safe resistor to make sure you do not burn out your LED or your diode. Okay. You have a potentiometer. You need to change the current to see what's going to happen to the LED. Okay. And for the voltage regulator, you also have the exercise 4, which you have an unregulated voltage source. Okay. You have the safe resistor to make sure you don't burn your zener. You have to calculate the value remember the safety factor. You put your Zener in reverse bias, okay? And you have your load, which you need to vary that. By variation of that load, you're changing the current and seeing what would be the performance of the Zener diode on regulating the voltage when your drained current is changing. And in another task, you are changing your input voltage, and you're going to see what's going to happen if we have a variation in the source. And is our Zener diode regulating our voltage at the output or not when we have a variation in input? Are we clear? Any question? I already uploaded some videos. There are some tips. This is the not very difficult kind of like tips, but I thought that it's good to mention. You have access to the PPT file in the Canvas page. So if you want to like go through that again, and I already uploaded the video of myself doing the exercise, the lab assignment 1 on the Canvas. Go through that. It makes your life much easier. Okay. So try not to just copy paste what I did. Okay. So try to kind of like work on the circuit. So you kind of like gear up, because after the first 3 weeks, we are going to start actually designing more challenging kind of like circuits. Then you need to have more understanding about these stuff. Are we good? Okay, thank you very much, and have a great rest of the day.